In this prototype, we are going to write a version of the game of tic-tac-toe that evaluates the core winning conditions, assuming that the board is of arbitrary size with arbitrary numbers of players. The winning condition is 3 consecutive symbols, and there is some weighting process, and so you can win in multiple ways, and you have to weight, across the diagonal is worth more than down a row. You have to do some sort of weighted average there. You can see this is not altogether unreasonable for a problem that seems really simple to start. Tic-tac-toe, 3x3 board, X and O, and then suddenly evolves in some strange ways. And we can see some places where original prototypes of the very simple version might extend to this, might still be applicable, and other prototypes might lose that applicability, might fall out of their ability to handle this. And so if I think about this, let me start with some dummy data. It's often the case that in order for me to do a prototype, I need to have some sort of concrete starting point. It is so often when we're doing some sort of analytical problem that somebody comes to us and they ask us to answer some question in pandas, and you really just have to show them some dummy data and say, wait, is this the pattern you want? If the data looks like this, is this what you anticipate seeing? And so let me hard code a board. Now I have a n by n board. And here's one area. Do I trust them n by n? Does that mean 4 by 4 is okay, but 3 by 4 isn't? I don't know that I actually trust them, that rectangular boards aren't allowed. So I'm actually going to write this as a rectangular non-square board just because I want to make sure that it works there, because I can easily see somebody interrupting me in the middle of the night saying, when we said n by n, we just meant arbitrary size by arbitrary size. We didn't specifically mean a square. And I don't know that I'm willing to bet my weekend that that's the requirement. Now here, if we look at the win conditions that I've encoded, I've got 1 down the column, I've got 1 or maybe 2 down the diagonal. I've got 1 across the row for O, and I've got 1 down the column for O. And so here, probably what I want to do is I want to take every window of a particular size. And so my choice to kind of jump ahead to NumPy instead of modeling this as a built-in type may actually pay quite a bit in dividends here, because it's a little bit easier for me to do something like get numpy.lib.stridetricks, windowed. We might have to look into that thing and see what's in there. From numpy.lib, import stridetricks. And to get windowed views of this data of a particular size. So what is this called? Sliding window view. So I think that allows us to generalize this pretty well. And I think the idea of writing this as a generator actually also works pretty well in this case, because here our function that takes the state and the symbols, and here we'll write this like this, is, let's just yield nothing. Let's write a simple piece of code that we can very quickly iterate on. And I think that gives us our framework. Another thing that you can see is I believe in an incremental approach, and I believe in a very specific incremental approach. I want to be able to write 1 line of code or maybe 2 or 3 lines of code and validate that they are correct in no more than 1 second of time. A fast iteration loop is the key to working quickly. Here's something that you may notice if we ever talk about JavaScript. I'm not that great of a JavaScript programmer, but I have really nice, fast prototyping environments set up in JavaScript. And so oftentimes when I don't remember exact syntax, I just try it one way, see if it works, try it the other way if it doesn't. And the really fast prototyping actually frees me from having to memorize a lot of the associated details. And I even do that with pandas. I can never remember, is it swap_levels, swap level one word? But I have a fast prototyping environment. I just try one. If it doesn't work, I try the next one, and I move on with my life. And maybe over time, I get some muscle memory built in. And so here I have just enough working code, and I'm going to try and transition from working state to working state to working state. Well, what I know here is, and I better materialize this structure, because otherwise I'm just going to keep getting this representation of the computation. So let's materialize that there. And what I know is that I want to operate on a sliding window of size 3 by 3, because that is built in, or on size win condition size equals n, maybe we'll parameterize over that. So here I want a sliding window, and let's figure out what this gives us. Sliding window view. Let's figure out what the parameters are for that very quickly. So that gives us a so it gives us a sliding window view. It allows us to provide a tuple, so it can be any size. So I think 3 is correct. We actually want a 3 by 3 sliding window. So let's do this. And let's see what this looks like. And see if that's correct. And here, let's do 3 by 3. I guess it needs that shape. Okay, there we go. So we got that, and that. That's good. And so how many should it have given us for a 4 by 5? It should have given us 1, 2, 3, 4, 5, 6 sliding windows, and that's what we see here, except you can see a little bit of extra unpacking that I probably have to do. So I think I need to unpack this one more level to get each of those independently. And then I can actually reuse my previous code that just identifies, whether you won within a certain square, and I could do a yield from. So I could even go back to a previous prototype and reuse that code. And that's always great whenever we're able to reuse previous code. So this is a win condition on a particular block. And this is the win condition. This is a win condition on a block. And this is the win condition on the whole state. And what we can do is we can say yield from, or maybe we can just do this for now, yield from the win condition on this particular block, given the symbols. And let's see if that worked. And of course, we need to change this here. The naming is something that we can change separately. Of course, we need a couple of imports here, diag and fliplr. And I believe, we need our classes from before. And this is where maybe it's the case that some of the work that I did previously is less useful because it now requires that I, bring a lot of stuff over. I bring all of this mechanism. But I think this actually worked. It says that the left diagonal has a player X. Yep, that's right. And then it says that there was one on the row. That's right. And you can see now I probably need to supplement each of these classes with some additional information, like which block it was, or what the top right location of the block is. So maybe there's another parameter here. And you can see where if I had already written some code that had been consuming the output of this thing for scoring purposes or for recording purposes, here it would be valuable for me to use these data classes, because then all of that code just gets another entry in it. So here, let's do this. And this is a case where we can say from itertools import chain, and we'll actually do this. We'll chain from iterable this, and then we'll enumerate that to get which block identifier we have. So I won't say this is the best code in the world, but I think it works. Of course, we need to make sure that we add in our extra criteria. And you can see here, this is where the data class is getting a little bit clumsy, because I need to specify which block I'm in, which block identifier. And I believe that was the second parameter I passed. And so maybe this should really be some sort of locator. That's where we start to say, are we going a little bit too deep in the object orientation? Do we need this to be something that is itself a data class that represents the location of the thing, which could then, for the case of diagonal, be like left or right plus the block identifier? Assuming, for example, we might have some additional dimensionality here. But where I push back on that a little bit is, again, I'm willing to bet my weekend that the hierarchy of locations for where you can win is going to be some outside container and then some inside record, but there's not really another level that you can add to this. Because even if you make it higher dimensional, that just identifies which block you're looking at. And I don't think you need to have any additional axes. I don't think there are any axes where you can't encode this. So I think this is actually fair enough as a set of assumptions. Now here's something important. I am always very clear about my assumptions. If I'm feeling very generous, I'll even document them, but at least I'll have thought them through. Because I definitely want it to be the case that when somebody comes to me with a new requirement, I can give them a firm estimate of, hold on a second, I'd considered that, I'd ruled that out, I wrote my code assuming that I'd ruled that out. Oops. Now I'm going to have to do a lot of work to accommodate that new requirement. So now I know that we have really a very fixed hierarchy of the locations for where you can win this game, a block identifier and an identifier specific to whether it's the row, the column, the left diagonal, the right diagonal. And beyond that, if you have some sort of three-dimensional diagonal, you would just extend the diagonal, so that's fine. But if somebody had some sort of deeper embedding in this, like for example, you could play multiple games simultaneously, then I would say, ooh, that's going to require another structural change. Make sure that we account for this in the amount of time and the amount that we bill for this appropriately.